Okay, sorry about that. My internet got disconnected for a minute. So okay, let me share my screen again. Okay. So I was here the last operation. I need to I think this shifted to 4, 8, 16. Okay, so this is done. I was saying here we are done because we have done the last operation here. And of course, this is my multiplicand. So if I convert this to decimal, this is 2, 4, 2, 4, 8, 16, 32, 64 plus 6. That is 70 decimal. Okay. Now, the reason I wanted to do this twice, because if you notice, there is something here whenever I made this addition, when I add this number, let's say I add 0, 0, 0, 0 here. This is add plus 0, 1, 1, 1. The last bit here, the most significant bit, if I add 1, 1, 1, and 0, my carry out, I should add one column here. This is my layout. And I want to insert, right? Okay. I will call with this add operation. There is my carry out. Okay. So here, after every add operation, I added 0, 0, 0 plus 0, 1, 1. That's the first add. Here, that's the carry, is 0. Actually, I can move it to the... So the carry here, when I add 0 plus 1 is a 1, 0 plus 1 is a 1, 0 plus 1 is a 0. So the 0 here, that's why I bring this, when I shift to the right, I have to bring the 0 to my partial product. The next one also here, when my next operation, and of course my first operation was just a shift, there was nothing, and here there is only a shift. Here, shift, I don't care about that, but the last one is add and shift. Here, there was a 0 with a carry. So when I add 1 plus 1, 0, 1 plus 1, 0, 1 plus 1, 0, and then 0, the carry is 1 plus 0 plus 0 is a 1, so the carry out is 0 here. Okay. Why I'm saying that, this will be clear in the next slide. Let me go to this is going to be the same numbers, except that now I want to reverse this. I will make this the multiplicand. I will make it 1 0 1 0, and the multiplier I will make it the 0 1 1 1. So nothing changes. I am adding and multiplying 7 times 10 or 10 times 7. The associative law tells me that this should not change the results. Okay. So now, and this is my partial product. Now my first operation here, my first operation is not a shift. This is going to be add. So let me delete all of these. This is fine, the multiplier. Okay. That I will leave it in a second. So I will keep these ones so I could reuse them, my arrows. And here, delete this one. And delete all of these. And also, I want to delete these. Probably I will use them again, but let me start fresh. And here, uh, okay. Let me just check if I am recording or not. I hope I am. Is my okay, I am recording. All right. Okay. So now my first operation is an add. So I have to add, as we said, I add the multiplicand plus the partial product. And here I will just say it carry out. Okay. And okay. I'm just trying to make space for myself. Okay, so now I will look at my multiplier. My multiplier here is 1. So my operation is going to be add multiplicand plus multiplier. So I will add here. I will say plus 1010, and the result is going to be 1 1 0 1 0, and the carry out here, the carry out is 0. So that's my carry out from this operation. 0 0 plus 1 is a 1, 0 plus 0 is 0, 0 plus is a 1, and the carry out is 0. And here is the multiplier continue to be the same for now. And I will bring it down here. Okay, so this is now my partial result, 0 1 0 1 0, and here 0 1 1 1. So I need to do the shift now. Here I will say shift right. So I'll shift right this guy, all of it. So this 0 will come down from here all the way here. So now I have 0 0 1 1. Actually, all of them now are black for now. Okay, so I do now this one. So let me take this one out here. So this one is gone. I can put it here. So this one. Okay, so that all of this is step number 1. So I added 1 0 1 0. So I got the result. Now I shift this. And of course, now I need to shift the partial product. So that 0, which is this 0, comes in here. So this 0. Now 1 0 1. Now that 0 already left to the other side. So now let me bring this arrow. Okay, so that's where I had my new partial product, 0 1 0 1, and this is 0 0 1 1. So now this one for my second operation, now, I look at this bit, I find that this bit is also 1. Now it's 1, so which means this is add multiplicand plus multiplier. And actually I will just say without the word add, this is confusing me, and just MD plus multiplier. And Okay. So now I need to do the add. So I'll bring this multiplier. This multiplicand, I'm sorry. This is it right here. I add it to the partial product, which is 1, 0, 1, 0, 1. So I say plus 1, 0, 1, 0. And the addition here, I have 5 plus 10, that's 15. So all of these will be 5 4 ones. So this will be the result, 1, 1, 1, 1. So 1 plus 0 is a 1, 0 plus 1 is a 1, 1 plus 0 is a 1, 0 plus 1 is a 1. So that's my new partial product. And I will bring this one also down. So this is my 0, 0, 1, 1. This was my initial red. I keep it red. So now I have to do the shift from here. So I do the shift right. And note here, when I did the addition, 1 plus 0 is a 1, 1, 1, 1, and I don't have a carry out. So the carry out is 0. This will become obvious when I go to the next step. So this is my second addition. So this operation is done. We finished this. I have my partial product. Oh, I need to shift, right? I still have not shifted, right? Sorry. So the shift now, this will be 0, 1, 1, 1, and this last one will move here. We'll have a 1 and 0, 0, and a 1. Now this 1, 0, 0 remain black. Okay. So when I do the shift right, that's what I get. Again, I will notice that my my 0, the carry which I had it carry out, which was 0, nothing. So I put it 0 here. So now I got step number 3. Step number 3, I also have the add operation because I have a 1 at the last one right here. So this is going to be multiply plus multiplicand plus partial product. So here I will have 1, 0, 1 plus 1, 0, 1, 0. I will add this. So let's add them. And this is 7 plus 10, that's 17. So I do have a carry out. So it's 1, 1 plus 1 is a 0, plus 1, 1 plus 1 is a 0, and 1 plus 1 is a 0. So these will be all zeros except the first one. So this is 0, 0, 0, 1, and I have a 1 here, my carry out. So that's my carry out. So this is the result of adding 7 plus 10 is going to be 17, which is 17. However, this carry goes into the carry out, and the result which remains in my partial product 0001. Now, if I did not keep this carry, if I did not notice this carry, I will definitely have a wrong result, and you can test it for yourself. So now I have, this is my result. So this guy is still 1001. Okay. Now I'll have to do a shift right. When I shift right, now this one comes from the left. Then I have 1 0 0 3 zeros, and this one comes here. 1 1 0 0. So that's the result of my shift right. I am done with step number 3. This is my partial product now. And of course, I have here my multiplicand was 1010, still 1010. I did not change it. The fourth step, which is the last part of my sequence, I look at this bit, which is 0. That's my 0. That's my bit. This is a shift only. I don't have an add. So I shift right all of this stuff here. Now note that this one with this shift, after I have done that with 1001, now when I do the shift alone, that's not a result of addition, so I don't have a 1 here. So now this is a 0. Oops. So after I do the shift, so note that always when you have a shift, operation without an add, you will always shift a 0 into the most significant bit. Why? Because if I had a 1 before, this one would have been shifted here, as we have seen earlier. If I had a 0, so that 0 would have been shifted, and then I cannot bring a 1 from outside. So this is how it goes. Now, so let's do the shift now, the last shift. So I have a 0 from here, coming from outside, 0. And this is my 1, 2 zeros here. And the last 0 comes here. So let me bring this. So I have my 0 here. And of course, here I will have 1, 1, and a 0, and that 0 goes out. So this is my last operation. Sorry. So I have 2 zeros. So this is my final result. If we look at this number, it's exactly the same as before. So this is 70 decimal, which is the correct result. Now, if you did the same thing, except that when you were doing the shifting to the right here, if we did not bring this carry out back, we will have absolutely let's say if I inserted a 0 here, your result will be totally off. It will not be correct. So that's one caveat you have to look for. Now I think this 0, there was a shift here. Where do I want to put this? I think it was here. Yes. Okay. So this is the multiplication of any two numbers. This is multiplication. We call it unsigned multiplication. Unsigned. We don't look at the result whether they are plus or minus, positive or negative. We'll just call them unsigned multiplication. Unsigned integer multiplication. Now, if we want to do a signed multiplication, we have two different ways of doing the signed multiplication. Two different ways. One way is to take these numbers. Let's say, let me take the same thing here. Oops. Let's say I will do the signed multiplication. So this is, let's say, plus 7 multiplied by minus 10. So what we will do in this case, we will complete the multiplication as is. And once we are done, then we will check the sign. So let me put that, show it in a block diagram. So again, this is the signed multiplication. So I'll have the my registers going to look like this. This is my multiplicand. And this is my multiplier. And I will have a signed bit. Sign. And this is the sign of the multiplier. So this is 1-bit register. So after we do the multiplication, see the multiplier here, and this is now in my block diagram of the multiplier. As we had earlier. So this is my multiplier. And this is my multiplicand, I'm sorry. And this is my multiplier. And I have my partial product. When I am done with the multiplication, This is my final result. That will be fed from this guy and from this one. And the sign so actually I don't need this. I just need this one. And so we'll take the from here and take the sign. And this sign, of course, is the exclusive OR. If both are ones, then it's positive. And this is the sign, the operation. So this product sign of product, call it. And here I can write the sign of multiplicand. And this is the sign of multiplier. And here this is the sign of product equals sign of the multiplicand exclusive OR. I think I had an exclusive OR function somewhere. I believe if I go to the adder, yes, right here. Exclusive OR, the sign of the multiplier. So this sign of the multiplicand, I will take this sign of the multiplier and this sign of the multiplicand. I feed them into exclusive OR. So if they are different signs, then it's going to be 1, 0 and 1. It's going to be 1. If they are the same, if they are either ones or both ones or both zeros, then it's going to be plus. So that's how we do the sign multiplication, which is not necessarily bad, but it's extra operation. That's what we usually say. That's extra operation. One guy called Booth, the Booth algorithm, he proposed, let me go, this is just to show if I do a 32-bit multiplication, which is going to be the same. We are not if we have both 32 bits, then my results are going to be 64. bits. Now, as you can see here, my final results, actually, I don't need a new register. All we need probably is to concatenate the PP and MR, but the result, if I want to get the result, then I feed them into a final result of the multiplication. I put them in this register. But if I look at my result finally in the PP and MR registers, and I will have the shift right. Remember in our previous example when we had the diagram, this will be now of course the sign here for the final result. I will get it from the MR alone. It's 1 bit, and from the multiplicand 1 bit, so the PP and MR can be concatenated. I can have this result. So this shows that it's like a shift right. I don't like this, but anyway, that's how it is. I could have done the line from the PP to the MR as a right shift here, but at the end, when I want to send my data to the memory to store the results back in the memory, remember when we talked about the ALU at the beginning, we said there is this big accumulator, this system which consists of, the only thing I have is an add and shift. Add and shift can be always accomplished with an adder and a shift between the registers. That's it. So that's what we have. Now, once we have this result, we can take it and send it to the memory as either two 32-bit registers. Actually, if I want to go into the memory design, so we can look ahead into our system, how it will look. Just sneak into memory design. My memory, this is the memory. Okay. One more layer. No matter how much your register size is, each memory is 8 bits. It's 1 byte. It's 1 byte. Okay. So all are 1 byte each. So for a 32-bit register, so we'll take these okay, as one register if we have 32-bit. And of course, if we have 64-bit register, then we will have all of them as one register. So one register will be, if it's 32-bit, we'll send them 1 byte at a time, 4 bytes. They will go into this location, this location, this location. So this becomes my multiplier, and my multiplicand will go here. And if I have the result, complete result, so if I take these, okay, so this is my total 64-bit uh, uh, multiplication result. And this one is my multiplier or multiplicand, 32-bit register. If I this will take the 32-bit multiplier or multiplicand. So my memory doesn't care because my memory is organized as 1 byte. So if you register the multiplier is 32 bits, you need 4 bytes of the memory. If it's my result, I store it in 8 bytes. And when I want to get this result to multiply it or add it to something else, I'll retrieve 8 bytes at a time here. So that's the way the memory. So we don't really care about the size of register, except in the sense that I will be able to multiply larger numbers and get the results either. So if I don't have a register in my system, my CPU, that holds 4 bytes, then I will not be able to do the multiplication in one shot. I can break it into multiple operations. That's fine, but in general, for 64-bit, for 32-bit multiplication, I need either uh, a register which has 64, which has, actually, this is wrong. This is not 1 byte. This is one, that's 4 bytes. I need 16 bytes of these, 32. Oh, sorry, no, 32 bits. Sorry, 32 bits, that is 8 bytes. So that's correct. 32 bits, that's 8 by 4, that's, no, it's 4 bytes. I'm correct. 4 bytes is 32 bits and it's a register. And 8 bytes, that's 64 bits, 64-bit register. That's correct. So with 64-bit, if I have a 64-bit register in my memory, then I can do 32-bit multiplication. And with the 64 bits, I can store it in my memory in 8 bytes all the time. And that makes our life easier. Let me go into, that's what we are doing here. So I have 32 bits for multiplier, and the multiplicand expanded 64 bits. The multiplicand itself, we expanded into that's for the result. And that's my 64-bit ALU. I put my product into 64-bit register, but this 64-bit register, we have to move it into memory 1 byte at a time, because our memory will not be able to store 2 bytes at the same time, because the data bus, if I go back to my memory here, this memory usually has the two buses. One is called the data bus, and the other one is the address bus. Okay, so this is one, and the other one is the address bus. So if you are sending data to the memory, you can the address bus will find one location in the memory at a time. You can't find two locations because you will have one address, and this address goes into the memory into a byte. It doesn't go into 2 bytes. But the good thing about it, if I have an 8 bytes, I will send the first byte here, the address of the first byte, then the next one will automatically carry an increment of 1 until you get an 8. So you go from 1 byte, then you go to the next third, and the next, and the next, until you finish 8 bytes. So that will make it easier. I don't have to send 8 addresses to the memory. I send one with a control saying this is going to be 8 consecutive bytes. Okay, let me proceed. This is just explaining what I have just said. Now this is the multiplication, the regular multiplication, which we have just done. I am just multiplying 2 multiplied times 3, it's going to be 6. And if I am going to do the sign, I will just do the plus and the minus independently. So that's not something I want to repeat. Okay. Now this is just the diagram for the multiplication. If I have a multiplicand here and a multiplier here, and this is my partial product, which has P1, 2, 3, 4, 5, 6, 7, 8, and the multiplier and the multiplicand. See, this is my multiplicand M1, M2. Actually, this should be M3, M4. There are 4 bits, and we will be doing this the summation. This is an adder. That's for bit number 1. When we had this add, I'm adding and the shifting. So note that this is an add, and there is a carry goes into the next stage, these carries, and the sums come here into the partial product. This is just to show the mechanism of how all of this multiplication is done. And this is, of course, the add operation. That's an adder. So all I have is an add and shift, nothing more. And this adder can be sequential. I can do 1 bit at a time, or it can be parallel, which means I can add all the numbers at the same time. But in our case here, for 4-bit multiplication, I will do the adder into 4 steps. I will have 4 adds, and some of the adds are going to be just shift without doing an actual add, which is we can substitute that with an add 0. So we will not miss on this clock. So with every clock, I will have an add. But if the least significant bit of the multiplier is a 0, so it will be an add 0. That's equivalent to no add. And then continue with the shift after that. Add multiplier, add multiplicand, or add 0, and then shift. Add 0, shift. Add multiplicand, shift. That's all you have to do, and you will do that with a counter, a 2-bit counter. That 2-bit counter will allow you to do 4 steps. And if you are doing an 8-bit multiplicand and multiplier, you will do a 3-bit counter. And here is I have a clock because if I have a clock, that means my multiplication is synchronized. I'm not going to perform the multiplication with the next sequence, because the counter can be digital logic. So I wait, there is an N here, so that I know what's my next sequence. And there is a counter, so if my counter is 0, when the clock comes in, it fires my current N. So my N here can be 0, 0, or 1, 1. If it's 0, then I look the product, which is the for my partial product, either add like note that add 0 and shift, or add 1, or the add is a 0, which means you don't do the add, or just add zeros. And the one you perform an add, and then you perform a shift. In order to do add and shift, your N, your current N, and then the first most significant bit, which is P1, or the least significant bit of your multiplier, has to be 1. Then you do an add and shift. If it's 0, then you just do a shift. And then the next step here, when N goes to 1, that's the N is on, of course, here. If N is 1, which means you have a clock coming in, and you have the counter, this some counting here, so you can get your control signal is 1. So if it's 1, it's again depending on P. So if P1 is 0, and of course if N now is 2 or 3, 0, 1, 2, 3, the same thing. With each level of N, you are going to have 2 variations. Either do an add and shift like this 1, 1, or you can just do the no add and the shift. That's the same diagram. And it's just showing the step 1 add multiplicand, and then which is S plus MD. S, that's the partial product, plus MD, and then load result into the partial product. And step 2, you will do the same thing until you are done. Okay. So multiplication with sign, I already talked about this. Multiply the two magnitudes through 32 iterations if you have 32 bits, and then neglect the result if the signs of the multiplicand and multiplier differed, or negate the result. If the result, usually you assume it's positive, but if the signs are different, just make it minus. This is another way, better than faster than doing the exclusive OR, but the exclusive OR also is, which I mentioned earlier, that's a technique which is commonly used, and it's straightforward, because you need an operation, at least one operation. So you are not gaining here when you say, when I want to negate the result, usually I assume it's positive. The result is positive. If the signs differ, so I have to check the signs, and to check the signs I have to look at the exclusive OR, which is the best function I have. Okay, this is alternative method, which is called the Booth algorithm. So the Booth algorithm continues in the same manner as before, except that in the last operation, it checks if the least significant bit of my result is 1, we will just do one more subtraction. Subtraction is add with 2's complement. If the number is 2's complement, then we will add it. So let's see how it works. So if I look at a number like this is 1010 times 0011. I assume that my numbers are in 2's complement. So the 0011 means it's plus 3 in 2's complement. And the 1010, it's actually minus 3. So 0 keeps the 1, and then this is 1, and this is the sign. Oh, I'm sorry, this is minus 6 in 2's complement. If you remember from your basic operations, going back here, well, let me reminder of 2's complement. Now let's say if I have a number 1010, so you keep the right digit, the first one to the right, 0. This is because the sign is 1, the most significant bit, so this is a negative, and then it's 110, which is equivalent to minus 6. If I have it 1000, then this is equivalent to minus, again, you keep the same numbers as 1000. It turns out to be minus 8 and plus 8 are the same. So if you have also, let's say 111, I think this is minus 0001. So this is minus 1. Okay, so this is the 2's complement. We remember these things. So now let's see how both algorithm looks like. We start with iteration 0. Now my numbers, the 1010, if this is my multiplicand, which is, and my multiplier is 0011. This is my multiplier here, and that's my product. Let me put all of these as blacks for now. Now the product, my partial product, I put 5 bits here because the 5 bits, I may need the 5th bit because of the sign. I have to, because remember, this is 11010. It's a minus 6. It's minus 6. Okay, so let me take all of these now. Okay. All right. So I initiate my counter to 0. I look now at my least significant bit, which is on my multiplier, which is here. This is 1, so now I can mark it with red because I know what I'm doing now. This is, whoops, didn't take it. Oh my. All right. So this is 1 here. So And this is my multiplicand, so I need to add. So least significant bit is 1. So my product equal product plus multiplicand. So this is my product. So I add, now my product, of course, is all of it, 0, 0, 0, 0, 0, 0, 0, 1, 1. So I add my multiplicand, which is 1, 1, 0, 1, 0, and I put it in the left-hand side. Okay, so it's 1, 1, 0, 1, 0. I add it to the zeros. I keep the same thing, and then I bring my initial product right here. So this is, now note that the addition here, I am adding the all zeros to 1, 1, 0, 1, 0. And this is 1, 1, 0, 1, 0. Remember, it's minus 6. I'm not saying I want to subtract, but if you add a number to a 2's complement, it is like subtract. So this is 0, 0, 0 times, or add plus 1, 1, 0, 1, 0. This is because this 1 is negative and it's in 2's complement, so I'm actually subtracting minus 6. But it's an adding plus minus 6. So that's what we are doing here. Now, once I am done, I do the right shift product as usual. So I take this product, all of it, and I shift it to the right. When I shift this to the right and bring the, and here you will see, so this is my product. That's my product. I need to shift it to the right. So I have it now. I have to shift it to the right. Everything shift to the right as usual. So this is a shift to the right. Everything as usual, except for the least significant bit, the 1. I check if my least significant bit is a 1. So I keep it 1. I don't shift a 0 into it. I shift a 1. Okay, so that's after I do all the addition here. So I added multiplicand plus all zeros. So I have 1, 1, 0, 1, 0. Now I want to shift to the right. I shift 1, 1, 0, 1, 0. It's right here. That's the 1, 1, 0, 1, 0. Let me put them in a different color here. Let's call it blue. And these ones, that's my blue. So I shifted my blue here. But this one, the first one, I move it here. I keep it. I shift it to the right, but also I keep the 1 because I want to keep the sign because my sign is negative, so I will keep the sign. So now I am here. Now this is my multiplicand still the same. Now my next product, I will look at this 1. I have a 1. So again, I will do an add. I will add 1, 1, 1, 0, 1. Add it to 1, 1, 0, 1, 0. 0 plus 1 is a 1. 1 plus 0 is a 1. 0 plus 1 is a 1. 1 plus 1 is a 0, and the carry is 1. 1 plus 1 plus 1 is a 1, and the carry out, and we don't care about the carry out. It's gone. Now, remember the carry out, if it's 1, it doesn't matter because still my number is negative. Now I do, so that's my result of the second operation. Now I will do the right shift. Right shift, so the 1, 0, 1, 1, let me put this in blue again. This is my blue. And here is my blue. 1, 0, 1, 1, 1. So that's my shift here. And again, this one is preserved. And this is the genius discovery of Mr. Booth, which the algorithm is named after him. Okay, so I'm done with the second operation. After I did the right shift, now my least significant bit here is a 0. So now 0, no operation. I don't do any operation. As if you remember, going back to the earlier here, when 0, no operation. I just said, don't do an add, don't do anything. Or if you want to add, you just add zeros. So now my n is, and P1 is no operation. I will just do the right shift of the product. This is my product now. All of this product, mine. So this is my blue. And when I shift it, it goes right here, becomes 11011, and this one, this which is, it's really the sign bit, but we don't use the sign bit as before. It's not in a different register, it's part of my number. So it's right here. Now, the least significant bit, again, it's a 0. So this 0, so it's one more shift. So we don't do any operation, we'll just right shift product. And here is my product again. 3 ones, that's my product. 1, 1, 1, 0, 1. That's my yellow number. And we shift it here. 1, 1, 1, 0, 1. That's my 0, and that's my 1 right here. Okay, so I right shifted the product. So now it's 1, 1, 1, 1, 0, 1, 1, 1, 0. That's my product in negative. So this is with my sign is 1, so it's a negative number. If I want to, and it's in 2's complement. So if I will do my 2's complement reverse, I want to find out what's the real number. So I'll take the first 0 and 1, I keep them unchanged here. Those ones, I leave them unchanged. Let me put them in red. So they are here. These are my first. I move from the right to left until I face the first one. Then I flip every other bit. So I have 1, 1, 0, 0. The 0 is a 1. The 1 is a 0. All of these are zeros. So my number actually, it is 2, 4, 8, 16, 18. And because it was minus, so it's minus 18. So this is minus 18 in the decimal, which is correct. That's minus 18. So all I have done here in my multiplication with the negative signs, I can do that minus 6 times minus 3, and I will get plus 18 for sure, because I always preserve my sign. So if my first sign is 1, I keep the sign, because if I change it from 1 to 0, which means if I do the shift here, when I did the shift, actually I shift everything here, 1, 1, 0, 1, 0, as we said, but then instead of inserting a 0, I always insert a 1. It doesn't matter whether my carry out is 0 or 1. Actually, the carry out is ignored in 2's complement addition. So that's how we do the Booth algorithm. It's good for multiplying the signs without actually dealing with the signs independently. This is the same example here. Is it? No. This is actually two negative numbers. This is a good example. So let's look at this example. I am multiplying 10 times, I'm sorry, this 1010 in 2's complement is -3, is -6, and 1011 in 2's complement is 101 is -5. This is -5 times -6. The result is +30. Let's see how we get the +30. Okay, so let me here get this in a more visible fonts. So again, this is my multiplicand, which is the 1101, which is the 2, the -6. That's so this is my -6, 0, 1, 1. Now I added one more bit to the sign that makes it okay. So now this is my product 1011, which is the -5. Here 1011, that's my product, and the 5 zeros as usual. I start with all 5 zeros. Now I check my first bit. First bit is 1, so let's mark it with red as our convention. No, not all of you guys, only one I want. Okay, now so I have a 1 here. Because I have a 1, I do add. So I will add 11010 plus all the zeros. So the result is 11010. So this is my result. Now I will do a shift, right shift. When I do the right shift, so this one will go out and the next one will move to the right and it's going to be red also this time. And then the 0, 1, 0, I'm shifting here from these guys, the 1 goes out, so I have 101, 0, 1, 0, 1, all of this, and then I'll add the I'll keep I'll keep as much as possible my why this is not coming. I will have to borrow one from here. Okay. So the one, when I shift right, I shift everything right except the first bit here. After I do the shift, I keep. So as I was doing it, this is my blue. And this is my blue also. So I shift all of these, but the least significant, the most significant bit remains unchanged. The 1 remains 1. Now, again, I have a 1 here, so I'll do a add. I add the 11010 to this guy, to 3101, and then the result 1 plus 0 here, this 1 plus 0 is a 1, 1 plus 0 is a 1, 1 plus 0 is a 1, and then I will have the 1 plus 1 is a 0, and there is a carry. 1 plus 1 plus 1 is a 1, and then there is a carry out. I don't care about the carry out now, not like before. If I had it 1, then I have to bring it back. So I'll just ignore the carry out. So now this is my result. I will do the shift, and the shift now, we shift all of this to the right, and it will go here. Note that my results are moving slowly to the right. So now my least significant bit, my red bit is 0. So I'll just do a shift. So I shift all of this. No, not this one. Sorry. I'm going to shift this guy to the right. And I will keep the most significant bit unchanged, like here. And one more. I keep this. Now the last bit here is a 1. Okay, so I'm done with the right shift. Now the least significant bit is a 1. So with this one, we will do the product equal product minus the multiplicand now, which is now my multiplicand is 11010. In order to subtract it, I will convert this back to its complement and do the addition. So 0 plus 1 is a 1, 1 plus 0 is a 1, then 1 plus 1 is a 0, 0, 0, and you ignore. So that's what we call the correction in this case. And of course, we have to do the right shift of the product as before. So this one goes out. So my is 10011. And I shifted this to the right. And this 1 goes out, and I remain with 0. So now, because I've done my last operation here in the 2's complement, my last operation is going to be a subtract rather than an add, because this is correction for our results. We kept keeping that until the end so that our product becomes correct. If of course the last bit is 1, if it's 0, it's going to be a shift. There is nothing changed. We don't do anything. If the least significant bit is a 1, we'll just do a subtract from this final result, which is the multiplicand now 11010. We will inverse it first, take the 2's complement, put it back, it becomes a 6. Now remember, our product was minus 6. So this is 6. I got it back. So if I add 6 to this result, then my result is going to be a positive result for sure, because what we have here. So we'll get the two numbers. The multiplication got positive. All these zeros, 1, 1, 1, 1, 1. That is what, 14, 28, I think. No, that's 13. 15 times 2, that's 30. So this is plus 30. So last iteration with a negative multiplier in 2's complement. If the multiplier is negative, okay, that's my the multiplier was minus 5. So that's my multiplier 1011. It's negative. And this one is negative, so we can do the inverse, the minus instead of the addition. So remember, this is both algorithm, and it's a very interesting algorithm. And most of the system today, they do use both algorithm for negative, for signed numbers. There are quite few which they don't bother about both algorithm. They just do the sign multiplication alone, independently, as I've shown in the previous example. Now, the last thing I want to do today, it's an interesting thing. This is, do I have the parallel array? Okay. So this is adding partial products. So this is parallel multipliers. Now the notice here, note, if I'm going to add, to multiply two numbers, x and y, where x is 4 bits and y is 4 bits. So if I will do the regular multiplication, so it's x0 ended with y0, ended with y1, ended with y2, ended with y3. And then I go to x1, I will get y0, y1, y2, y3. So I write x1, y0, x1, y1, x1, y2, x1, y3. And there is a carry, of course, from x1, x1, y3. There is a carry out. And then if I go to x2, I multiply it by all these 4 bits. Note that the multiplication of 1 bit at a time is equivalent to an AND gate, which is, I think I have it here. Yeah. 2 input and a full adder. So this, any xk with any yi, okay, I just feed them here. That's my result of x ANDed with y or multiplied with y. It's 1 bit. So if I will take this example and just okay. So let's say, let me write instead of x, instead of y, I'll say this is 1. This be 0. And this is 1. This is 1. And let's say the x is 0, 1, 1, and a 0. What happened to my 0 here? Ah, Okay, that will do it. Okay, so if I have this, then I will have 0, 1 here. 0, 1 is a 0. 0, 0 is a 0. So all of these are going to be zeros. 0 and 0. And this is a 0 also, because that's what? That's 0. So I have 0, 0, 0, because this is 0, and here also, these are all zeros. Zeros. And here also is a 0. And the last bit is also a 0. Now, if I do 0, alone 0, 0, and the next one is all ones, 1, 0, 1, 0, 1 ended with a 1 is a 1. So this becomes 1 and 0. Anything ended with a 0 is a 0. And then you will have 1 here. And also the last one is a 1. And here they are all zeros. Zeros, 0, and a 0. So this is one way of doing multiplication. Give me any two numbers, 16-bit or 32-bit numbers. I will have the AND gates. Now, of course, the first one doesn't need an and the last one doesn't need. No, the last one, because of a carry, it would. So I have 1, 4, one AND gate, two AND gates, three AND gates, because if you have only two input AND gates, so you can count how many AND gates you will have. So here you will have 0 partial product. So the first result is going to be a 0. And here 0 add. Now this is an add for partial products to be summed. 0 plus 0 is a 0. 0 plus 0 plus 1 is a 1. Now note that if I have here 1 and 1, so you will get a carry out. You will get 0 carried into the next stage. And here you have 4 zeros. So your result is 0. And here I have 0, 0, 1, 0. Your result is 1. And here 1, 0 is a 1. And finally, 0 is added with nothing. So this is 0. And you don't have a carry out. So this is, you don't have any carry here. This is 0. So this is your result, which is, what is this? 2, 4, 8, 16, 32, plus 16, that's 48, plus 4, that's 52. So you can easily verify this 52. Instead of doing the multiplication as we did before, you will just say, okay, let's do the ANDing of the corresponding numbers. Get the partial product for 0, which is 4 bits. Get the partial product for the next 0, which is all zeros. Get the partial product for 1, which is equal to the multiplicand. In this case, 1, 1, 0, 1. And the last one, this is your multiplier, this is your multiplicand. And then add the corresponding bits. Make sure that you don't miss these bits together. And the good thing about this is if you will do the array multiplication, What you can do, we can do the parallel. So the first one, I will bring the P0. Then the next operation, x0, y1 plus x1, y0, I do the partial product. Then I will, at the same time, so I have a sum, an adder here, which is adder, it doesn't just a register. I have one adder for these two. I have one adder for these two bits here. And I have an adder for this one with the carry that comes from here. And I have here, again, three adders, two adders, one adder, and one adder. So you will, and they will be, the addition will be done in parallel. And if we use the ripple carry, adding the carry from the final stage needs an extra, the ripple carry stage, or they can be with the look ahead adder. If you use the look ahead adder, then you are done. So the idea here is I can do my partial products instead here. I had to do 1, 2, 3, 4, then 5, 6, and then together 7, then 8, 9, then 10, 11. There are at least 11 add 11 adders here. Or 11 additions. Okay, so if I do the additions in sequence, this is going to take very long time, and most likely longer than the add shift multiplier, which we have seen before, because of the carry, not for anything else. Whereas if I do the parallel here, carry is added to the next partial product, which is carry save addition. I can save this carry, and I can later on put it anywhere I want. Adding the carry from the final stage needs an extra ripple carry stage from here, because the last one, it's not like the first stage. The first stage does not need anything else. The last one, although it's 1 bit, but if you have a carry from the previous stage, so you need an adder here. So you need an adder here for sure. That's 1. There are 2 here, unless you have a carry from the previous stage. Actually, if you have 3 bits here, let's say if they are 1, 1, 1, if all of these bits 1, 1, 1, yeah, you will have a carry into 1 plus 1 is a 2 plus 1, it's 1, 1, so you have 1 carry into the next stage. But with the 4 bits here, you will have 2 carries out from these 2 bits. And if you have a carry from the previous one, then you will plus 1, so you have 5 bits here to be added. So let's get a bit complicated, but you can organize it always, so you can make as many parallel additions as possible. The basic building blocks, as we said, this is the AND gate, which gets this bit, 1 bit of the partial product. So with this AND gate, how many ANDs here? If you have 4 by 4 for multiplicand 4 bit and 4 bit for the multiplier, you have on the order of 16 adders, because everyone need an adder. The x0 need an adder here, 1, 2, 3, 4. The x1 has 4, so it's 16. 4 times 4, that's 16 adders you need, definitely. So this is number 1. Assuming that I have 2 input AND. If I have more, well, actually, even if I have more in like a bigger input ANDs, which have multiple inputs, more than 2 inputs, that's not going to help also. What will help eventually with the adders. So you need the 16 AND gates. So these AND gates, and then with every AND gate, an output with AND gate will go to a full adder, and there is the sum bit from the k minus sum. So you need from the previous one of the sum, you can bring it to this adder here. And this sum bit to the next stage. And there is a carry bit, because this sum bit has to be summed with the other bits after that. And the carry bits also, we need to take care of them. This is the basic design. So step one, get all bit by bit multiplication. Use the property 0, 0 is a 0, 0, 1 is a 0, 1, 0. All of them are zeros except the 1, 1. So that's a property like I have just done before. So if I have x0, y0, I can build this matrix. It's a matrix where I find x0, y0, x1 is ANDed with x, with y0, with y1, y2, and y3, x2 again with all of these, x3 with all of these y's. And if I have the, as I said, I did a minute earlier, I have 0, 0, 1, 0, and 1, 1, 0, 1. I will just do this 0. All of these bits are going to be 0. All these bits are zeros. All of these bits are the multiplicand, 1, 1, 0, 1, and all of these are zeros. That's the output of them. And then you do the addition here. That's the array multiplier will look something like this. This is my starting from my x's here. So this is my x. x0, x1, x2, x3, and these are the 0, 0, irrespective what x is in my example, x's were 0, 0, 1, 0. So this could be 0, 0, 1, 0. And then you will get the y, these y's. So the x here so I like the red colors better than the yellow, which is not visible. Okay. So the x now, x0 is intersects the y's here. And each one, this is comes from x0, this so this is x0, y0, this is x0, y1, and this is x0, y2, so this is x0, and this is x0, y3. So these AND gates, the first AND gates, which give me these guys, x0, y0, x0, y1. So we have them right here. Now, the first one goes directly to P0. I don't need to feed it to any adder. The next one, x0, y1, this one, is added. There's an adder here. It's added to this result, which comes from x1, y0. If we look here, there is x1, y0 is ANDed with x1, y1 is ANDed with x1, y1. So if I go here, so this is x1, y1. What is it? This is x1, y1. So let's see, x0, x0, y1. I add it to this guy, which comes from here, which is y0, x1. That's x1. That's x1. What is my second AND gate? X. Let's see. This is x0, y1. x0, y1. And this is actually, let's go here. x0, y1 is ANDed with x1, y0. So I go to x1, y0. This is x1, y0. So they intersect here and here. So this is the one right here. This is x1, y0. And I add it. This is my adder in the black box. That's my adder. I add x1, y0 to x0. This is x0, y1. So if I put this x0, y1, and if I can decrease the font so it can be visible. Okay, so this is x0, y1. It's not seen to you, but I can see it here. That's x0, y1 for me. And then the rest we don't have the AND gates, but this x1, y0 right here, this one, this will be another AND gate like this one. It's x1, y0. And this here, it should be like a carry from previous stage, but we don't have any carry here. See, where do I have? And this is of course a carry, which is not which is 0. We put it as 0 because it doesn't have a carry. This is the carry into the next stage. This is all these carries into next stage. And this one is coming from x1 alone. This is x1. Okay. So we have the x1, y0 here from the first stage. I have x0, y0, x0, y1. I have x0, y2. I have x0, y3. And those, the AND gates coming from here. And then we will add x1, y0. And I will have the x1 feeding here also. From all of these, the x1 is feeding into all of these adders, especially if I have the 0. So the 0, 0, 0, 0 here. And I will have 1, 2, 3, 4 multiplied by 4, that's 16 adders. 3 times 4, the 16 full adders. And at the end of these adders, the first one will get me a P0, the second one will get me a P1, then I will have 2 adders here, will give me P2, the next 3 adders will give me P3, the next will give me P4, and so on. So this is and if you count this, how much the cost of this multiplier, you will calculate, you have 16 AND gates plus 16 adders, and these adders, of course, they do have their cost, but you will have 16 plus 16, that's for 4-bit addition, for 4-bit multiplication. It's a bit expensive, but you can get your multiplication in almost as fast as the adders can produce results. Now there are different types of multipliers. Well, Booth multiplier algorithm, we said there is 3 multipliers, and there is this signed product by 2's complement, addition or subtraction algorithms. These are the different algorithms. This is going to be October, I think 10. Now the binary division, actually I will do the binary division. I will give it maybe a few minutes. It's the best way of doing the division is to have the division inverse multiplication. So you'll just like x divided by y is x multiplied by 1 over y, and use your multiplier. And there is, of course, algorithms for division anyway, for the unsigned and division. And the signed, you can do the division like the adder in 2 different ways. Okay, so next time I will finish all the ALU, and then I will go to the next step, to the memory organization and the virtual memory and the cache memory as for the architecture. And once I am done with the ALU, I will give an assignment using the Logisem simulator. So we will be using that to have one project for the ALU design. Okay. Think any questions for me, guys?
I did have one question for the assignment.
Yeah.
Um,
Previous assignment.
Did you just want us to show the work, or did you just do you want us to make like a circuit as well, or is it just like do the add shift and then show the work for the arithmetic?
Let me check the assignment. What did I have in there? Give me 1 second.
It was a 4-digit multiplier with the 6-digit
Ah.
for the byte, 6 bytes.
Oh, no, I did not want you to do the circuit. Just do the table design, which I have just done today, okay?
Okay, thank you.
Just do the table, show the steps one by one, like the add shift, or shift alone until you get the result. Okay. That will be good enough. I'll do the design
Okay, thank you.
for the full circuit, as I said, as when I finish this ALU, I will ask for one. It's a project light. I will give you 2 weeks for that, or 3 weeks to do circuit design, complete circuit design. But for now, no, just what we have, as I mentioned. Okay.
Yep, that was everything I was wondering.
Okay, anything else? Anybody has any other question? Okay, I will just give I will make another assignment now for the multiplication with both algorithm. Usually I like to make sure that we understand the both algorithm with an assignment. And I will see you next week, guys. Okay, okay, have a good afternoon or good night. Actually, I'm already in a morning time. My time shift now is almost 3 o'clock in the morning. Okay, I stop share. All right.